Hi everyone, this is Ari Danish and welcome to Houdini Light, Shade, and Render, Module 7. Today we're going to talk about the Mantra renderer engines and more specifically how it goes through its rendering pipeline. So before we get started today, just one little quick diversion I want to show you. So let's go to our shell. When we start up Houdini, and I'm working on a laptop as I record these. I think I showed you before, I can go -J and then say how many processors I want dedicated to Houdini. So I could do something like Houdini fx -J space 2, and Houdini will come up with only 2 processors running and allowing it to have the other 2 processors for things like, well, recording this video or background tasks. So I want to show you something else. Let's say if I want to use for simulation all of Houdini. So I loaded up Houdini here. And might as well start up a scene. So what's today's scene look like? This guy right here. Cool. So it's just a simple cove with a camera, a box, a torus, and a sphere. And I want to render this out. But I want to make sure that the rendering doesn't take up all the CPU time. Can I do the same thing with the -J space 2 that I did for all of Houdini, just for the rendering part of Houdini? And the answer is yes, and let me show you how to do that. So what we're going to do is we're going to go to our out context, and let me just kill these mantras nodes and start a new one. There we go. If we look at Mantra and look at its parameters here, you'll see there is this line called command. And if I click on the drop-down menu for it, you'll see that there's actually a lot of pre-built commands for it. So, network rendering, verbose output, there's one called use one CPU. And when you do that, notice you get the -J option here and a 1. So if I have a 4-processor machine, I could say dedicate 2 processors, for instance, to it, just like that. And now I have the other 2 processors, so I can continue with Houdini, or I could do other background tasks. Okay, so let's find out what we're going to be learning about today. So I have here the syllabus for today, and you can see that we start with our little diversion here. The next thing we want to talk about is, what if I don't want to render within Houdini? Can I render at the command line? And the answer is yes, and we'll learn how to save out an IFD and then render it. And then, I'm giving you a really brief overview in this hour of the Mantra pipeline, and I'll show you some links on our side effects website to get a more detailed learning of the Mantra. And then we're going to talk about viewport speed versus render speed, and then some refinement, which is the first step of the rendering pipeline. Then we're going to talk about, should I just, instance wherever I can? And maybe sometimes it's not the best thing to instance, and we'll talk about that. We'll talk about bump maps versus true displacements, and then we'll talk about, render buckets, coving, opacity, shading, and jitter. So, okay, let's start up. So as I said, I have this little cove. That's all we're going to need for understanding what's going on today. And let's go to camera 1 and go to Mantra, which we are at. And let's just see what this quick render is going to look like. Okay, and I notice I didn't save something for you. So let me quickly fix this. You guys didn't see this. Go here. L to my torus object. There we go. Okay, so I got this very crude torus, sphere, and this box. So back to the output. Okay, so right under that command file, you'll notice that there's something here called dist file. And I could select the dist file right here. And I could save it out. So, I could save it out to my HIP folder, which is, right here. I could give it a name like testme.ifd. And remember, And IFD is per frame. So if I'm doing an animation, I might want to go underscore $sign, F3 or F4, whatever is going to work for you. And then all I have to do is go and render. And if all went well, and I open up my folder here, Dish, LSR projects, module 7, I should have a testme 001.ifd file. Now, if you look at this guy, let's open it up in BBEdit. And IFD is a combination of HScript plus binary data. Okay. So you can actually put in your own HScript commands wherever you want, and it will execute just fine. But more importantly for us is that I can go to the command line, wherever the command line went, let's find out where it is. Okay. So it looks like close my shell. So let's just go here, CD to module 7. Let's do an ls. And there's my testme.ifd. Cool. Let me clean up my window now. Excellent. So all I have to do now is give it a command line, and the way I could do that is do something like mantra, and then redirect, for instance, to whatever I call this, testme underscore .ifd, and if I run it, mplay should come up. And render out the file for me. So I was not in Houdini at all, was able to do it in the command line. And yes, you could do it in the command line even if you have the apprentice version. Okay, another thing you could do is give it another name like mantra and redirect testme. And this time give it your own name like foo.jpg. And it should render out, and let's do an ls. And I should get a nice foo.jpg right here that I can open up. So let's just double check and make sure that worked. And lo and behold, it worked. So you could, output any image format, just use the right extension like PNG or EXR, and mantra at the command line will render it out. Cool. So as I said, this is a really brief overview this hour. So where can I get some better information, more detailed information on the pipeline? And there's really some great material out there. One is really old. It's from Houdini version 9.5 called, it's under the master classes section of our tutorials. So if you just go into learning tutorials and you go to the master classes right here, you'll be able to find, a master class in mantra rendering here for Houdini 12. And if you keep on going down, you'll find different versions of it, starting with 9.5, that go through the entire pipeline in detail. And I highly recommend that you go through these videos. In the PDF that I send with this weekly class, you can see that I put all the links in there for you. Okay, so one of the things we got to talk about in rendering is the viewport speed versus rendering speed. So obviously I have here this torus, and when I did this, live, I had a person saying, we really need a lot more divisions on here, and that's true. But the question is, what do I want? Do I want Go to the scene view. If I had thousands of these, do I want to be able to interactively go around my viewport, or do I want to see a really pretty picture in my viewport? Always a compromise. So what you can do is, for one thing, you can say in the viewport I want it really low poly, but then if you go into your torus object under rendering, you can go right here. You'll see it says polygons as subdivision. And when you click on that and then go to your render view, you can see that it will do the subdivision at render time. So is this a good thing or a bad thing? And that's a good question. There's no right answer, but I think most of us kind of went through school and they always said that, remember, always model with as little polys as possible and let the render engine, subdivide and clean things up and make it look smooth, because bottom line, we want things to look smooth. Well, that might not be the best solution. It might be, but you got to understand what your scene is doing. So what do I mean by that? Let's see if I can give you an example. So the very first stage of the rendering pipeline is refinement. So what is refinement? Well, refinement, bottom line, is it has to take every poly that we see here in our scene view, and the goal for any renderer is to say, I need to render from this point to this point with a nice smooth gradation depending on the light and the shader. And if we were to do that, and maybe I should put on smooth wire shaded. Okay, so it's going to have to go through this vertex to this vertex and calculate how to smooth it. Well, the way it does that is it actually takes this poly and subdivides it, and then says, can I make a smooth shade between this new vertex and the next new vertex? And if not, it subdivides it again and subdivides it again. And this refinement process can be extremely costly as far as render times go, because for every frame, it's going to be recalculating that. So let's go back here to the render view and see what's going on in our render. So I'm going to turn off, let's turn off preview and auto update. And I'm going to then hit pause right there. Perfect. So when we render, you got to remember that the render engine is rendering in buckets. Okay, these little tiles here are called a bucket, and it's basically saying, let me just load up this amount of geometry or camera space and render just this independent of each of these guys. So that means if I go into the sphere here and look at it, I got this little bucket. It really doesn't know anything about this guy, so it's got to subdivide it until each of these guys is basically pixel or smaller for it to be a smooth gradient. So I think I have a graph for you. Yes, I do. So here I take this cube and I got this one big poly on this side. So what's going to happen is it's going to subdivide this one big poly into 4 smaller polys, and then it's going to look at one of those 4 smaller polys and say, can I be smooth or not, or can I render it smooth or not? If it cannot, it then re-subdivides this into 4 more polys and 4 more polys and 4 more polys down here until it gets its smooth gradation. Then it has to pop up to this level right here and subdivide it, and when it's done, subdivide this section and then go to each of these tiles in reverse. So it's doing this like really massive for loop to calculate all this. It's not actually a for loop, it's actually a BSP tree, but bottom line, it's got to loop through everything. So how can I help this process become much quicker? Well, you could say, well, maybe I could instance all this geometry. And you remember how we instance. We could go here and just do a really simple instance of, let's say, this sphere. So I'll just drop down an instance op. And in my instance op, I will drag and drop what I want to instance, which is my sphere object, and say fast point instancing, and then move it wherever I want in the transform. So let's just translate it a little over. And while I want to see this, so let's go back to the instance. I'll make this just off so I can see where I transformed it. Great. Let's move it forward a little. I like that. And then I'll go here and say fast point instancing. And when I go to my render view, I guess I should hit home. I get my instance object. I must have hit the transform somewhere because it's not where I thought it should be. But okay, so we got our instance. Now, what happened here? Well, in the refinement stage, it looks at a sphere, at this sphere, and says, okay, I got to subdivide it and make it smoother and smoother. But the problem is when I instance, this is in a different position, it could be a different orientation, and therefore looking through this camera, these polys are not in the exact same location. Therefore, guess what's going to happen? It's going to have to refine this instance also. So if I had 1,000 of these guys, I'd be refining 1,000 spheres. That's going to take a huge hit in rendering time. So instancing might not be the solution for everything as far as rendering speed. So what else can I do? Well, you could do your refinement stage manually by yourself. So how does that work? Well, remember, it's going to subdivide and subdivide until it can render smoothly. That means if I subdivide my object manually beforehand while creating my geometry, it doesn't do it during the refinement stage. So let me show you how to do that. So let's take a box, and I get scene view. Just going to drop down this box here. Let's bring it forward so you can see what's going on. Now this box, if I were to instance it or make multiple copies, it would go through a lot of refinement to make it smooth. But what I can do instead is, looking at this box object, I'll dive inside the geometry and I'll subdivide it myself. I'll go tab, subdivide, and I'll wire it up, and voila! And you're going to say, that just sucks. It's not a box at all. And you're correct. But what we can do now is, in the subdivide SOP, you'll see that there is a checkbox for override crease weight attribute for my subdivide. I'll turn this guy on and nothing happens. Let's go and increase my depth to what would be a refinement. So let's put this guy at 4. Okay, as you can see at 4, we now have a lot of polys. We might be able to render smoothly. We might have to even go up to 5 for refinement. And that by all means does not look like a box. But now what I can do is, with this override crease weight attribute, is I can go here and just increase it until I get the sharpness of the box that I needed. And I might want to go just a little down because, hey, micro bevels are good. And there we go. Now, when it comes to the refinement phase, the first phase in the rendering pipeline, you've already done this manually. So it's going to bypass refinement completely for this object. So if I go into now my instance, and instead of using that sphere, let's use that box object right there and render. It's going to render much quicker because it did not have to refine the second box here. It's been pre-refined. So again, it's something for you to consider of, if I have, a million objects out there, let's think I have a tree with a lot of twigs and all the twigs are the same twig, just kind of rotated into space and maybe a little scaled. Pre-refining it into a dense mesh might actually help your render times considerably. A couple things to know about this is once the refinement phase starts, polys must be reduced for each instance. We already talked about that. As of H12, all rendering engines use the same refinement stage. So that means whether you're in PBR, whether you're in micropolygon or ray trace, this step is in each of the render engines. So you don't have to say, well, I'm optimizing for PBR, I'm optimizing for ray tracing. When it comes to the refinement step, you're optimizing them for all. The other thing to know is that as of H12, the shading quality multiplier is shared also among the renderers. And we'll get to that part in a few minutes. So how do I increase the shading quality multiplier? Okay, remember the shading quality multiplier causes more refinement to occur. So all I have to do here is go to my out context, and in the mantra node, if I go into properties and I go into, I believe, dicing, you'll see this shading quality multiplier right here. Now, the more you increase the number, say like 3, the more subdivisions are going to occur in the refinement phase, so you get a smaller and smaller poly. For those who come from the RenderMen shading language, this will probably look familiar, but the opposite is true. In RSL, I believe the smaller the number it is, the more your subdivisions are going to be. Okay, so let me catch up my notes. And so really the moral of this story here is, remember, in large scenes with high poly counts, if you do manual refining, then instance objects are all the same through the rendering pipeline. That will make your renders much faster. Look through the camera. Try to have your polys of instances roughly the same size. So what do I mean by that? Well, imagine if I had this box here, and it's going way into the horizon. Well, obviously I don't want something that's only a couple pixels high up here to have a million polys. So what I want to do is kind of make sure that no matter what the distance is, that the polys are roughly the same size. So while I might have a few instances of the object up here that are really highly subdivided, I might want to use another instance object back here that only has a couple subdivisions because the objects are much smaller. So again, the idea is try to keep the poly sizes about the same size. And finally, what if I'm using displacement maps? Well, if I'm using displacement maps, all geometry then must be diced. If you remember, I think it was 2 weeks ago when we did that kind of slimy texture in Mantra, we had to put in some properties in our VOP shop to do dicing. And the reason why is we don't want these holes in our rendering. So regardless of refinements, we're going to have to go through the displacement cycle. So instancing is not going to probably help you, or I should say instancing could help you, but pre-refining your geometry probably won't. So what about bump maps? Well, if you use bump maps, there's no need for dicing, and that could be a huge render savings. So how do I set up so it doesn't do displacements and only bumps? Well, 2 ways. So let's go back to our object level, and let's just dive into materials and create a couple of materials. So let's use the material shader, the Mantra surface shader, I should say. Right there. And if I look at the parameters of the Mantra surface shader and I go to displacement tab, you can see that there's a sub tab for displacement maps and bump normal maps. If I click on bump normal maps and I just go map type to just bump, I can then check on use bump map right there, and for this material I completely bypass displacements. But to have displacements, I would have to enable it here. So that is if I'm using the Mantra surface shader. How about if I'm creating my own map? Well, that's even easier really, because I don't have to remember where to put it. So let me just go up here and drop down a material shader builder, dive in, and here is, you remember, where our displacement output is. And by now you should know that probably the node that's going to go right before this guy is a displace along normal. Let me drop that down, wire it in, and let's look at the properties for that, or the parameters. And notice in the parameters for displace along normal, sure enough, there is a bump only check mark. So that's how you do bypass displacements and just do bump onlys for your own shaders. Very straightforward. So let's just look at one more thing while we're here. I'm going to go up, and I believe we still have our Mantra surface shader right here. What happens if I do enable displacement maps? Okay, and you notice it says true displacements here. With true displacement on, instances become unique even before refinement. So once you put a true displacement on, you might have fast instancing, you might have full instancing. It doesn't matter. It's becoming its own copy because it's got to do the displacement on that copy. So that can cause, especially if a lot of geometry, a large amount of memory bloat, and can really slow things down. So just be careful of that. And again, when you use bumps, you use bumps. So what properties affect refinement? Well, we already talked about shading quality and displacement. Well, what if it's not a poly? What if it's a NURBS or a Bezier surface? Well, in that case, it's the level of detail in a NURB or Bezier. Dicing, the shader quality causes, an effect on refinement, and so does geometry measuring. So we haven't talked about geometry measuring at all yet, so let's go there. So I'm going to go back to my out context and look at my, I guess we don't need that right anymore. So look at the properties. Here we go. If I look at dicing, you'll see we talked about shading quality, but there's another guy here called geometry measuring. And there's three options for geometry measuring. There is non-uniform, which is measuring everything through camera space. As you saw, that is really what's the default is. Then there's raster space, which is basically screen space. And then finally there's uniform measuring. And uniform measuring generates uniform divisions. The size of the divisions is controlled by the geometry quality or shading quality in the micropolygon renderer. So this is a very quick way, if you have kind of a simple scene, to get all your geometry to have the same size micropolygons, and that might cause it to render quicker. But for most cases, just leave it at the default non-raster. Okay, so we were talking earlier about buckets. So if you remember, I went to here to render, and I hit pause, and I got these little buckets. Now, how do I affect the bucket size for rendering? That's real simple. That goes right in here into your render options. You'll see there's a guy called tile size. Okay, now I can adjust it, so let's make this like 64 by 64. And now if I render, you can see that my bucket size is much larger. So remember, each bucket is rendered independently of its surroundings. After a bucket is rendered, the renderer can throw away all the computed micropolygon geometry, saving memory. So obviously each bucket, the larger it is, remember the default was a 16 by 16 size. Now I have it as 64 by 64. So the larger the bucket, the more memory I need. But the nice thing is, the larger I have it, even though I might take up more memory, once I render this, it releases all that memory. So it actually might become, ironically, more memory efficient to have larger bucket sizes. If it's a complex scene, and it's doing a lot of calculations, you might have to have a smaller bucket. But you might want to play, especially if you have enough memory, increase the tile size and see what your rendering efficiencies are. They can actually improve with a larger bucket size. Okay, let's just, ooh, that kind of weird. There we go. Let's kind of look at one little diversion. And that is, if I go into my type properties, actually into my edit parameter interface, there you go. And we go into our rendering tab, and let's go mantra. That's good enough. If you want to see really kind of the rendering pipeline, start analyzing what's going on here. So we said, here's the dicing. We're doing refinements and all the stuff that goes on with that. Then there's, the atmospherics, the fog, the geometry. So if you look through the parameters that are at your disposal, you can really learn a lot about the rendering pipeline. We did a few of these 2 weeks ago when we did that slimy surface. But, go and really read up on what these parameters can do for you. Okay, that was my little quick diversion there. So the other thing I want to mention is I wanted you to visualize this. Because we are doing, let's say we're doing a true displacement, what I can do is I could displace along, this little poly up here going straight up. And then I could go through a refinement cycle and then displace going, let's say, in the X direction. And then do another refinement cycle and true displace along the Z. So I could actually create these little hooks that have no geometry involved at all. It's just specifically a function of the shader and rendering. This could cause huge memory bloat because you're doing refinement at every phase of the displacement. So again, moral of the story, a lot of times it's better to do your geometry, do your modeling at the geometry level than at the surface level. So what's the next phase in our rendering? Well, if I'll go back to my object level and take any object here, such as the original, box, and I go into the Geometry tab. So Render tab, Geometry. You can see that there is this phase called coving. So after refinement, we start to do coving. And by default, coving is set to displacement and subdivision. So it's saying only if I see an object that either has a displacement shader on it or we're subdividing with like a subdivide stop, do I want to go through coving. Okay, and that's pretty efficient and what you probably want for most cases. But what is coving? Well, coving is the process of filling cracks in dice geometry at render time, where different levels of dicing side by side create gaps or T-junctions. So what does that mean? Imagine, I got this complex geometry and the camera's looking at it and we're refining this area, and this area needs a lot more refinement than this area for some reason. Well, obviously we're not going to have that beautiful quad where all these polys mesh up with these polys. So what we can get is these holes in rendering. So coving is really kind of trying to stitch it all back together by filling in the cracks with more geometry or refiguring the geometry. So if you think about it, in that case, what makes most sense? Well, it's going to make most sense when I have displacements. And again, let's go back to that 2 weeks ago, that slime shader that we built. Remember, before we put the dicing in, we got all these black kind of spiky things going on in the render. That's the holes we're talking about. So once we go and say cove, stitch it back together, refine it, that's going to fill in the gaps. So it makes most sense for subdivision or displacements, but sometimes you're going to need to do it for everything. And that's what coving for all primitives does. So it allows us to say, hey, I'm still having holes I don't quite understand. Try this. Try changing coving to for all primitives and see if your holes disappear. Remember, when I say holes, it's going to look like is jagged black, maybe triangles, or kind of like a saw pattern. If you see those, just change coving for all primitives and see what happens. Okay, after the coving stage comes the opacity stage. So let's take a look at that. Let's just drop down a sphere, move it so it's kind of partially in one, and I'm going to just reduce the radius here. Probably don't need this guy, which was box object, so let's just delete that. So I'm going to just leave it like that. And I'm going to apply a glass shader to it. So let's find glass. And let's see if we can just apply it right here. Redo a render. That looks good. Let's just do one more thing. Just for the heck of it, let's go and put a pattern. And I don't have any UV set up for this box. It's not going to look good, but I just want something to interact with the glass. And let's see if I got that pattern to jump. There we go. Just so the glass has something to play with. Cool, we can see the refraction down here. And the key thing I want to show you here is, so when rays go, it's going to go and say, okay, this is transparent. And then it's going to go and figure out what is opaque and stop there. Okay, so this is another phase of the rendering pipeline. And what you want to see here is that it decides what is transparent, what's opaque on every vertice. So it's going to look at the OF part of the shader. And it's different than RSL because Mantra is optimized for volumes and fog. So all it's really doing at this phase is saying, is it either opaque or is it transparent? And anything in between gets tested further down the pipeline. So if I look at my glass shader, right there, you'll see, let's see where I can find it for you guys. If I go into opacity, there we go, you'll see that there is a opacity scale and it's set to 1, and that's really all you want, because either you want it to be 0, and when we get 0 we'll have, everything is perfectly transparent and you won't see anything. I'll just click on here to get there faster. Or you get 1, which is it's opaque and test for opacity. Which gets you a correct result. If you try to go and say, you know what, I want to see what the 0.5 value is, that's when you're going to run into problems, because now you're just completely destroying the opacity test. And let's do a full render of that so you can see what the result looks like. there we go. You can really see that we're kind of getting this inner bubble out of this one sphere, which is incorrect. So for most transparencies, you just want to leave the opacity scale to 1. Okay, so we're now finally up to the shading phase of the rendering pipeline. So remember, we're really looking at 3 different types of renders. We're looking at ray tracing and micropolygon, which are biased renderers. They're really not plausible. There's just too many guesses, too many cheats to make it a good render for realistic rendering. Then we got PBR, which stands for physically based renderer. It is a non-biased renderer, and it's very physically plausible. It's trying to go and get all the indirect illuminations correct. And the only thing I really want to say about this is, and I think I've said it before, and I'm going to try to hammer this into you, is that when you're using PBR, area lights render faster than point lights. So don't be afraid to use area lights in PBR rendering. They give much better results, much more realistic results, and to boot, they're much faster to render. So the next thing I want to talk about is pixel samples. So if I go back down here to our out context and go into sampling, we have this guy called pixel samples. Okay, and what is pixel sampling? Well, we created all those little micro polygons, and I'm going to zoom into this corner right here. And we're going to shoot rays out. And the question is, how many rays are we going to shoot out to test what is this shading? And so right now we have a relatively low 3x3, even though, you know what, at 2x2 in this scene would probably work just as well and be faster. There you go. Okay. So we're getting, well, you can see that actually it's not that good right here. It's getting us too distinct a line at 2x2. So we're getting these nice alias jaggies. We need to increase this by 3x3. And you can see I'm just going to go do a partial render by holding down my shift key and doing a drag. And you can see when I look at these guys, it's giving me a better anti-aliasing now. And the reason why it's giving me a better anti-aliasing is this guy right here, jitter. So if I set jitter to 0, I'm going to get a very 1980s clean look for my rendering. Because what it's going to do is it's going to throw these samples at very uniform distances apart. And therefore what's going to happen, as you can see, is I get a very consistent look, a very sharp, clean edge. As soon as I go here and change this to 1, what I'm doing is I'm literally making some noise and where these pixel samples are going to be rendered from. And that will give me a little more chaos and therefore a little more like smudging of the line, which gives me a more smooth, clean look. So I think I have some nice graphic for you. Yes, I do. So here we go. So jitter equals 1. You can see this row specifically, how we're getting, two guys that almost look the same, then a medium gray, then a little lighter, and even a lighter gray. Here, look at it. It is perfect step size. If it's like banding of a perfect gradient. Okay, and this will really show up in your renders. It will not look that good because it will be too sharp and clean of an edge. And 2, if you're having an animation going on, it will create a lot of video buzz. So, as your spaceship is going through, you'll actually see a little sizzle as if you oversaturated an image, but it's not oversaturation, it's just too clean versus, randomizing your color sample just a bit to get rid of it. So bottom line is you really want jitter. I can't think of anything except for you wanted a kind of a retro look that you would change this to 0. You don't need to change it to 0.5 or 1 or 2. 1 will work just fine. Just want to say a couple things more today and then we're done. And that is, when do I need to increase pixel samples? So if the geometry has a lot of detail or texture sample, or the texture sample has a lot of high frequency noise, increase the pixel sample. So there's a lot of displacement detail here, or if you got a lot of here, that's a good place to need to increase your pixel sample. So what I did here was showed you, here's a 2x2 sample, and you can see how kind of crude the line is here, how sharp the line is, not much of a gradation. I increased it to 6x6 and really zoomed in, and you can see I'm getting a much finer, much smoother, natural look. So this guy is, just a sphere that I displaced every polygon, and therefore it hits this part of a lot of detail. Again, if I had a displacement map, which had a lot of texture sample at a high frequency, so it's, kind of think of it a lot of little micro cracks, or I have a picture that has a lot of fine detail on it as the color map, that's when I need to increase the pixel samples. And finally, in PBR, pixel sampling is tied to allowable paths. So if I go into the PBR tab, I guess I got to turn on PBR. You'll see allowable paths. And so right now you got specular and diffuse passes or all paths. So right now it's going to do a 3x3 or whatever pixel sampling you have on the specular, and then another 3x3 pass on the diffuse pass. So that's 9 samples times 2 for each of those paths. If I now go into all paths, then my bump pass, my reflection paths, everything is going to go through this pixel sampling, causing a huge memory bloat and much slower rendering time. So for most cases, you do want to keep this at specular and diffuse paths. And that's all I really have to say today. I'll see you next week.